So what's A2O? A2O was the follow-on to A2I, but it was really meant to be a companion rather than a replacement. So by targeting different applications, the cores were meant to be able to coexist in a single system to meet customer requirements. And the big difference is that it targets workloads requiring high single thread performance versus A2I was more of a streaming overall throughput design. And the A2O core largely retains compatibility with A2I external interfaces to the memory and interrupt and other logic. But the big difference, especially for us at IBM, is it's written in Verilog rather than Vhdl. So it's taken a little while for us to get used to that. As soon as I find my slide, I'll advance it. So I discussed a lot of the A2 history in the A2I talk, and I won't go into many details here, but A2I was the processor used in Blue Gene Q, and this is the picture of the mirror system at Argonne that was retired at the end of 2019, but it lasted 7 years. So it had quite a long life of use and high reliability. This highlights some of the features of the cores. And as I said, the big difference obviously is the I versus O, which is in order versus out of order. And SMT4 for A2I, whereas A2O, at least in the original design, was only expected to be at most two threads per core. Okay, I must not be sharing charts. Let me figure that out. Okay, so here's the picture of Mira. So here's a high-level chart of the A2O processor core. As mentioned, it was designed for single thread performance rather than throughput, but the same overall goals of balancing performance and power and keeping the modularity that A2I had designed in with configurable accelerator, MMU, microcode, and such interfaces. As I said, the Verilog RTL is the big difference for us. And I think some people will for sure obviously be more comfortable with that than Vhdl. This shows some of the kind of differences of applications you would expect for A2I streaming and network processing versus more intense single thread things like AI and autonomous driving. So A2O design features, another difference is that it was 207 versus 206 for the ISA. So a small step forward, but still book 3E, two-way SMT, four-way fetch, two-way dispatch, and four-way issue, out of order dispatch execution, and G-share branch prediction. The caches were doubled in size, so 32K I cache, 32K D cache, same 64-byte line, single cycle access, and they also had a special prefetcher built into the data side. to handle out of order. It has a 32 entry completion buffer, and then it has a 16 entry load store queue. The modular design is very similar to A2I, with these interfaces being selectable as to whether a certain core would implement the features or not. And same as A2I, also supported big endian and little endian. So here we have a block diagram of the A2O core. As I said, the I and D caches are double the size of A2Is. The instruction buffer, microcode engines, renamers, and completion logic are all duplicated per thread, and reservation stations sit on top of all the pipes. And I think on the bottom right shows that there's also a prefetcher for the D cache. And same as A2I, the RAS, test, debug, performance monitor type logic is all built in already. This slide lists a lot of the same features as the original slide I showed. Not much more to say about it. Like I mentioned, it was also designed for 27F04 as A2I had been, so it could run at the same clock frequency. Some of the details of the top of the pipe, as mentioned, 64-byte iCache, 16-entry ERAT, which is a piece of the TLB. It's local. 16-entry instruction buffer, 18K bit hybrid branch prediction, 8-entry link stack, and rename, dispatch, and retire 2 instructions per cycle. And the reservation stations had a unified scorecard, a separate reservation station per execution unit, and each reservation station can accept up to 2 instructions per cycle. The oldest instruction issues, when available, sources, includes restart support for flushing, 16 entries per queue, and data forwarding between pipelines adds 1 cycle of latency for all operations. And for GPRs and the various special purpose condition code type registers and link register and count, full bypass. On the back end, the load store unit had a 32-entry ERAT. It's stored through cache, which is same as A2I was, non-blocking, hit under MIFs. Had the same back invalidate support as A2I also did for snooping, so it was ready to be attached to a SMP type environment. L1 hit was a 4-cycle load to use, 16-byte load store support for the accelerators and Dcache, software line locking and way locking, with an 8-entry load miss queue and a 12-entry store queue. The store queue is a big difference from A2I since that did not even have a store queue. It sent everything right out to the A2L2 bus. Intelligent data prefetching, learning strides for specific loads with a claim 95% accuracy. The fixed point units, 1 cycle latency for simple adds and subtracts. All other adds, subtracts, logicals are 2 cycles. Multiplies and divides only to fixed point unit 0 with a multiply latency of 3 to 6 cycles. A 2-bit per cycle divider that could end early. And then the branch unit also shared with FX0 to resolve 1 branch per cycle and handle 0 logicals. And then the double precision float, I imagine, was very similar to A2I. Not 100% sure, but besides the conversion to Verilog, I would expect it to be quite similar. So this is the card design that we did, very similar to what was on A2I. We used the same card. You can see from the utilization that we were way up there. This is an SMT1 generation. The Verilog has a lot of knobs to turn as far as controlling generation, and SMT versus single thread, or single thread versus SMT2 is one of those. So we didn't even get far enough, obviously, with this to be able to attempt SMT2. So even with putting the BRAMs in URAM, which we hadn't done for A2I, we were still way up there on LUTs and BRAM utilization. But besides that, the overall layout's very similar. We did not combine the A2O core with the A2L2 AXI logic, not for any real reason, just as it had started to be built that way at the top level. We just created those IPs separately. The BRAM and regs are identical. I think most of the AXI ILA things are the same. And the VIOs, again, we mostly were using to connect up, make sure that there was no unconnected logic, but also some basic control stuff for running the core on the FPGA. And again, we had no external interface except for the differential clock. So pretty simple design, and we definitely like to expand it a little, at least add on DDR, same as A2I. This is a scaling that we did, again, similar to A2I, pretty much the same conclusion. It gets pretty small in 7 nanometer and still can run at a high frequency. So we think it's still definitely relevant for some designs today, and for the same reasons of potentially mixing A2Is with A2Os and balancing different application loads to certain threads, etc. And this summary is also a lot of what I said on A2I. The big difference for A2O is that it never became an official product. So unfortunately, as designers, we usually don't do all the documentation until the tape out has happened and we're sitting around. So the documentation, a lot of it is obviously derived from A2I. There's been some updates, but there's definitely need for work, especially looking through the SPRs and a lot of the implementation dependent logic to verify that bits and fields and things are accurate to the RTL. So we'll be hopefully doing that with the community on the repo along the way the next few months. The other thing is there's not a huge amount of description of the interesting part of A2O in the user manual, which is the obviously the renaming, issue, tagging instructions, and all that completion buffer, all that kind of information is somewhat lacking in the document. So hopefully we can work to get a better understanding of what's happening in that logic. As far as adding things to the design, they're all kind of the same list as I mentioned for A2I of some obvious things just to help debug and do some stuff on the software side to get some better testing and validation as we do make changes to the logic. We really need something to be able to test against to prove we're not breaking anything too bad. So I didn't mention, but part of this project was also to work with a group of Extreme Blue interns, which is a special internship that IBM has, and wanted to thank them for their help. Did a lot of hard work, and we were able to get through the whole find the Verilog, update it to work with Xilinx, go through the documentation at least one time, and get the card up and running in 12 weeks. So as I said, there was a lot of things to get all that working, and thanks to Chester and Harsh and Aditya for all their work. And hopefully they'll join us on the forums to spread some of the knowledge they gained over these past few months. And just in closing again, everything is now open at OpenPOWER Cores A2O, and we hopefully will see a bunch of people out there and make some progress on using this core for any kind of interesting things in the future. So thanks for joining the presentation, and any questions can go ahead. So I see one question: why is it a big deal to use Verilog instead of Vhdl? Well, I'm not sure it is, but at least I believe some people think it is. Obviously, in IBM, we've used Vhdl almost exclusively. It kind of depends where you are in the world, I think, as to what your main design language is, but there definitely seems to be a fair amount of interest in Verilog designs versus Vhdl. So there's a question from Florin. On how to position an A2O design versus ARM for edge. I think that depends on your eventual application of it. Obviously, the big thing we would say would be the full power compliancy at the 3.1 level would be a big difference for the software stack and other things like that. But again, it's going to depend on your application for sure. And Luke asked what algorithm was used for out of order. I I probably can't even answer that right now. I have not been able to look too much in detail into that whole section of the pipe, even though I thought I would. It was one of the most interesting parts for me, for sure. I had worked the last 2 years on P10, and I was doing one half of the renaming and history buffer logic. So I would also like to look at that, but there's no way I can describe the tagging and things like that right now. Just haven't gotten that deep into the digging into the logic. And that's where I said the documentation was lacking, unfortunately. So it would be nice if we could try to understand that on the repo and add some useful information to the documentation. So we have a question from Jay. Asking about, will it run Linux PPC 64LE today? If that's the current level of Linux distro, then I believe the answer is no. I think it's been discussed that the latest Linux distros require at least some vector support, and the A2I and A2O Core both don't have that, even though it can be attached through the accelerator interface. It's not in the logic right now. Do I have any other ones? Looks like Luke asked how many instructions per clock. If that means how much it can complete per cycle, it was 2. So it looks like we're running out of time. We can meet on Slack for any further questions. It looks like there's a few more that have shown up. Does the value of the coprocessor interface change now that we have open source RTL? I think so. Obviously, if you can come up with a somewhat standardized interface, then you now have something to hook to any kind of special purpose accelerators you want to do that are tightly coupled. So yes, it would be, I think, a big benefit, and also give you a test platform. As long as you meet the interface, obviously you'll be able to test out your accelerator pretty easily. How does the core compare to microwatt? Quite different. The fact that it was designed as A2I was, and as a 27F04 pipeline, as was mentioned in the A2I presentation. The logic potentially is somewhat ugly because it had to meet the timing requirements. I believe microwatts, I don't know how many stages of pipeline it's doing right now, but it's obviously written at a much higher level than A2I or A2O was. Microwatt, though, will be ahead of these cores for sure, I think, in its ability to fully implement a compliant core, just because it'll be a little easier. Anything obviously added to do compliancy for these cores has to fit into the whole control structure and pipeline that exists. So that's a big difference for even understanding the core itself, let alone trying to implement anything fairly complicated. Replacing instructions and things like that would be pretty easy. That'll all be in some decode tables, but the farther you try to get into the pipeline, the harder things obviously get as far as implementing some of the bigger things. Radix, though, should be fairly easy to attach because it should drop in basically on the MMU interface. So that would be one place to start for sure. And it could potentially be done kind of without as many restrictions, since it's not tied completely to the pipeline. And there's obviously some signals that'll have to match up correctly, but a lot of it, as how long you take to do the translate, stuff like that, could be probably delayed or whatever to make the coding easier.